Okay, so good evening, everyone. I hope I'm audible. So let's start
Yes,
with
sir.
let's start with today's class. I'm gonna continue with where I left off in calculus. I guess I just kind of finished continuity and then was about to move on to derivatives. So derivatives, right? As we all know, there are that familiar concept of differentiation in one dimension, where differentiation can be like loosely it is the slope of the limiting second in on some curve y equals to fx in some coordinate axis. Okay, so suppose this is point p1 and this is point, or yeah, okay, like then I have to like move both of them. So so let this be p1, this be p2. So a second passing from both of them at this moment. Okay, so kind of like this. So as we are pushing P2 further and further towards P1, this line actually converges to some limiting line uh, to the tangent at the point P1, and that is and whose slope we call the derivative of this function at the point y. So as we know, slope is del y by del x. So naturally we have limit P2 tends to P1 del y by del x, which is, suppose this point is some x naught, x naught plus h minus. So that is one definition of derivative in terms of slopes. But this one is like a bit more difficult to generalize into higher dimensions, since we are doing a division operation, and divisions aren't defined in say suppose r power 3 or r power 4. So there is another definition using linear maps. So suppose we define, so first definition, and also this definition allows us to define two types of derivatives. One is left hand derivative and the other is right hand derivatives. So so left hand derivative is, so this thing here tells us that h is initially lesser than 0 but increases up to 0. um, Not necessarily monotonically, but the important thing is it like never crosses 0. So yeah, so this is the left hand derivative, and the right hand derivative is now moving on to the next definition of derivative. So so we want to be able to write something like this: f of x naught plus del x equals f of x naught. The value after slightly perturbing x should be more or less around the value of f of x naught plus some deviation that should be directly proportional to x del x, right? So some lambda times del x, or yeah, del x is okay, plus some error term like uh, r of x, r of del x. So the this del of x is our h, or whatever, the small perturbation in the x-axis, and this constant lambda is called, it's actually the derivative f dash x naught. This is not actually a constant, it's actually a linear function. So lambda of del x plus c, this, if we call this some f dash x naught, no, sorry, not f dash x naught. Okay, yeah, we can call it f dash x naught, but it actually takes del x also as its argument. So okay, so let me write it as, so in one dimensions, all linear functions in one variable are just of the form some mx plus c. Mh plus c. So here the function is f dash x naught, which specifies the lambda and c in this expression. And it takes an argument del x, and that del x here replaces the h. So in a sense, it is a linear function which maps from R to R. These kind of the space of this linear function is referred to as LR semicolon R. And since it is also continuous, like any finite dimensional linear map is continuous. So these spaces are called Banach spaces. Never mind. So the important criteria that like for f to be derivative, in the previous definition for f to be derivative, this limit just had to exist. If this limit had since there are two forms, the left hand derivative and the right hand derivative, both the left and the right hand derivative must exist for us to say the derivative exists at a point x naught. In this case, the condition is so the condition is limit h tends to 0, rh by h has to go to 0. This is also equivalent to saying small o of h. So like RH is of the RH is smaller than the order of h. That is, this thing happens. Okay, this thing is called the small o notation. There is also another big O notation. So big O of f is equal to g if so if g was a constant, so g tends to 0. Sorry, f tends to 0. Or if, say, suppose h of x naught is equals to some y naught, and hx naught is continuous at x naught, then limit x tends to x naught, g of x naught by h of x naught minus y naught. This should be finite. No, sorry. G of x minus g of x naught by h f of x minus f of x naught. Here in this small notation, the limit goes to 0, and in this big O notation, the limit can be anything finite, but it has to be something finite. So here it just says if can be represented as or the change in or the increment in the value of f can be approximated as a linear function of x plus some error, which is very small compared to the scale that we are measuring into, that is h. So then we can say f is differentiable at that point x naught. Okay, so now you can see we can easily extend it to higher dimension by using norm instead of modulus. So we say a function capital F, let me keep it small f from r to r power 3, say, suppose. Actually, they are all defined on some open interval I to some open interval u to some open interval v. So So f is from u to v. And for all x in u, we have norm of f of x plus. So there are two notions of derivative also again in higher dimensions. So this is the Gato one minus fx plus dv dtv. Let me give the Frechet differential. Yeah, so h and x are vectors in R power. Okay, here in this case they're still scalars. So h and x are scalars in R in an open interval u of R, and yeah, and dh is a linear function. So inside linear functions R to R power 3. So then this is a vector, this whole thing is a vector in R power 3. So whose norm has to be much smaller than the norm of, here the norm of h and h is the same thing, so this has to be much smaller than h. Had f been from R power n to R power m, then we would have used x vector, h vector. So this d was then a linear map from R power n to R power m. So the existence of this d confirms the differentiability of f. Okay, so this was the other notion of differentiability. Now let's look at some examples. By the way, this notion of differentiability is called Frechet differentiability, or just Frechet derivatives. So let fx equal to n c power n minus 1, where c is some constant. This is a real number. So f is from R to R. So what is f of x naught? Sorry, I mean x power, and then it won't have any sense. So let f be x power n. So f of x plus h minus x is Using the binomial expansion, it should be x power n plus x power n minus 1 in C1h up till h power n. X power n gets cancelled out. So we can now take n common. Oh, sorry, no, we can't take an n common now. Or the first term is nh x power n minus 1. And the rest of the terms all have at least h square in them. Right, so we can take common some h square. So when we divide it by h, this thing will still go to 0 if h goes to 0. So this is a small law of h term. So this thing is equals some nh x power n minus 1 plus small law of h term. So then rearranging we get so f of x plus h minus fx minus nx power n minus 1 times h. Norm is as good as modulus. This shows this is the derivative. So this is the linear map. Here in this case just a constant. Okay, a multi-dimensional case. Let's try a derivative of signum x. So signum of x is, as we all know, is 0 if x is 0 and 1 if x is positive. So suppose, obviously here on these points, it's differentiable since, okay, let's try to differentiate at any of the point other than 0. So let's differentiate at the point 1. So at x equals to 1, we'll use the first definition. So both of them are like very near to 1. So obviously if we can take h to be less than or h inside half to 3 half, then all of them are positive. So the numerator is 0 and the denominator isn't 0, so it's 0. Similarly, we will get the derivative at x equals to minus anything, also 0. Okay, so x is, so if x is differentiable at all other points except 0. At 0, let's see what happens. f0 we have sorry, I've been writing this wrong. So even then things had been like, sorry, right, 0 1. Okay, so now where f0 is 0, so it's just fh by h. And so fh is, since h is not 0, it's just tending towards 0, fh has to be 1. So its limit h tends to 0, 1 by h, which diverges to infinity. Right. So not differentiable at 0. So next, some complicated functions. Just a minute. Okay, so let's try this one. So let f of x be ax, where x is a vector in R power n, and A is a matrix in n cross R, n cross n. Just a minute. So x is a column vector. Okay, so it has to be in m cross n. So how to find the derivative? So we will use the second definition, which where we will get some d as the derivative, such that d of h is a linear map from the same space R power n to R power m. Here f is also from R power n to R power m, since the output of ax is in n. So therefore, let's first get rid of the norm. So f of x plus h so it's t of x plus h minus t of x, sorry, I mean a of, not of, actually a times. So since we from matrix multiplication we know it's a times x plus a times h minus a times x, which is just a times h, and that is already inside L of Rn Rm, right, plus 0. So 0 is already in O norm h, right? So that is derivative. So f dashed h, so x is a. Now let us try so here we have a inside it's an n by n matrix, it's an n by n real matrix. So this is also called a quadratic form. Okay, so suppose like if x was some x was xyz, this is the A matrix, A11, A12, A13, A21, A22, A23, 31, 32, 33. So then what does this look like? So first we have the 3 squared terms. Basically, to write it out more simply, you can write x, y, z here and x, y, z here. I mean x, y, z here, and then see how they intersect. So plus x a21xy plus a12yx, that is same as xy. So it's twice 821xy. Similarly, twice 831 xz, and twice zy, right? 823zy. So the whole sequence, the whole expansion is homogeneous of degree 2. So we can write it as f of x, y, z, such that f of uh, tx, ty, tz equals t squared f of x, y, z. So that's what we called homogeneous of degree 2. So expressions of the form x transpose ax, of course A has to be symmetric in that case. So if A is a symmetric matrix and the expression is of the form x transpose ax, then it's called a quadratic form. If A is if A is a complex matrix instead of a real one, then we replace this word symmetric with Hermitian. Then it has some certain desirable properties. We can discuss them later. So here we were to differentiate this. So f of x plus h minus fx, sorry, minus fx. So this is so let's first take this as a vector and multiply it with distributive using the distributive law. And now let us take this as a vector and then distribute it here. So transpose of A plus H is x transpose plus H transpose. So x transpose plus H transpose plus H transpose. Sorry. So that cancels out the first term. So H transpose AX plus X transpose AH plus H transpose AH. This is a norm H square. This has the order of norm H square since it's homogeneous of degree 2 as we just showed here, right? Or I guess we can show we can use Cauchy's inequality to show this is less than product of this is less than norm H square, some constant times norm H square. So this is our required derivative, which is also a linear function in H. Like all matrix multiplications are linear functions. To be a bit more rigorous, we can say let the dimension of h. No, we assumed it as n. Okay, so let h equals to h1, h2 up till hn. A vector in R per n, of course. And A is an n cross n matrix. So H transpose AH, this quadratic form is a bunch of squared terms. So AII HI squared INJ I naught equals J AIJ HI HIJ. Okay. So from a rearrangement in equilateral system. So first let us take the maximum. So let A star be the maximum entry of the matrix. The maximum overall ij. Let A star be the maximum overall ij. So then this thing is less than or equal to Aij times sum over hi squared plus sum over ij twice ij hij. Now we can use the rearrangement inequality in the second term to get this thing is less than or equals to twice of hi squared. Just a minute. How many terms are there? Okay, so what is the norm of h? Norm of h is norm of, need to show it is of the order of norm of h square. So right. So I'm kind of struggling to make it less than norm of h squared times some constant, since this the second term has like n nc2 number of terms. So we can't apply rearrangement inequality right here. So in case of r power 3, it was coming like only 3 terms. So rearrangement was natural. Now we need to apply something else, or else we can use another result that here we are using the L2 norm, right? The L2 norm, I don't remember if I have ever talked about these LP norms. I guess I have. So LP norm is defined as it's sum over items from 1 through n, xi power p power 1 by p. So p must be an integer between 1 and anything less than infinity. So if we want to write something as L infinity norm, this is equals to the, well, this is defined to be the max of xi. So we can use the fact, okay, the lemma. All LP norms in uh, in a metric space, in a metric space, or in a normed metric space, are equivalent. We call two norms to be equivalent, or we say, yeah, we can say norms also. So metric is the measure of is a notion of distance. So we can say the distance of between x and y as d of x and y. So we call this function d as a metric. So now if we have two notion of distance, d1 and d2, for the same set of 2 points, and these are like connected by some constants, like within the bounds of some constants. Getting so messy. C1 times D2 So two metrics d1 and d2 over some topological space x and t. Here in our case, x is r power n, and the topological space tau here is the space, is a topology induced by the Euclidean norms, that same topology, okay, also called the natural topology, and said to be equivalent if and only if C, okay, there exists C1, C2 in R such that for all xy in R power n, C1 D2 x1 x y C2 D2 xy. And similarly, you can take the reciprocal to show that uh, so taking the reciprocal, we have 1 by c1 d1 xy d2 xy. From these two, we have 1 by c2 d1 xy less than d2 xy. These two imply 1 by c2 d1 xy d2 xy is 1 by c1 d1 xy. So if any of these two conditions hold, then d1 and d2 are equivalent in that topological space. So here there is a lemma that um, okay, can I prove it now? Just a minute, let me think. This is the lemma that all LP norms. So a norm quite naturally induces a matrix. So suppose we have a norm, the normal Euclidean distance L2 norm. So we have a vector x, L2 norm is x, sum over xi squared, square root of that. And we have an L3 norm, xi cubed to the power 1/3. So we have to find the constants C1 and C2. So how to find them? Now we can compare both of them to the same norm, that is the L infinity norm, another norm of the same class. This is just the maximum, easier to deal with. So the maximum for xi. Oh, mm. So this thing is less than, I'm calling this x star, let me call this x bar or x cap. So now there are n of them. So this is the constant, n power half. This is our C2. To get the C1, so we need to find the lower bound. What is smaller than this thing? Okay. If we take just the x, so yeah, so the C1 turns out to be just 1. Nice. So here we have 1 times infinity norm of x less than L2 norm of x less than square root of n times L infinity norm of x. I guess this also similar thing also works for the L3 norm. Right, and then we can combine both of them to find the individual constants. So L2 norm we have to make it this thing should work, right? This is like nothing special for 2 and 3 in general. So 1 by n power 1 by q so the qth norm times 1 by n power 1 by q is less than or equal to the pth norm of x less than or equal to hence LP norm and LQ norm are equivalent in all Euclidean metric spaces. So how does that help us? Okay, so I was trying to show this thing is less than. So let me write it once more. So H transpose AH. We need to show this is of the order small h, small o of H norm. Yeah, this is big O. So we needed to show this is of the order of big O of norm of H squared. And we will use the L infinity norm since all the norms are equivalent, just differ by constants, like bounded within some constant multiple of the other. So now this evaluates to some over, as we have taken A star, I guess, to be the maximum of all the element entries of A. So hi square plus 2i hi hj. Now what to do with this term? So now we will use like this thing, that this thing is less than or equal to A star times sum over hi square. We'll replace it with h bar squared n times h bar squared. H bar is the maximum of all h. Plus twice, that is also n times h bar squared, which is equal to A star n, a constant, plus twice n times h bar squared. So this is as good as some constant times infinity norm of h bar of h whole squared. So we were successful in showing that H transpose H is of the order of capital O of H infinity squared. So we get the derivative of, what was it? X transpose AX. So X transpose AX has a derivative of X transpose EH plus H transpose AX, which is a linear function in H. So let's do an exercise. Okay, so now let fx or f a, let me call it x only. X is a x is in n cross n matrix, n cross n real matrix. So how to differentiate this function? So therefore f is a function from m n cross n r to x power n is also a same ordered matrix. So n is any number in natural. N is a natural number. Okay. So will any of you try it for a few minutes? There's a similar way. First write f of x plus h, f of x plus, since they're all matrices, I will use capital instead of small. So try and find the terms that are of the order less than norm of h. Those terms will contribute into the error. The rest of the terms, check if they are linear. If they are, then they are the derivatives. Okay, so what is x plus h? X plus h power n minus f of x is x power n. X plus h power n is x plus h times x plus h times dot up till x plus h. So n of them. Actually, sorry, like this n and this n have nothing to do with themselves. So let me call this m instead. So after expanding, we will get a term x power m, and since matrix multiplication are not necessarily commutative, so the rest of the terms will be of the form uh, 1x, then 1h, then 1x, then 1h. These kind of terms, then like either there are out of the m. So let me write them sequentially. So this one has 0 h matrix in them. Then there are terms of the form exactly 1 h in them, and then there are terms which have number of h's. So this is exactly 1 more than, sorry, more than or equal to 2. Okay, so and then the first term and the last one gets cancelled, and we have kind of a intuition that the third one with all h matrices more than twice will somehow be of the order of big O of norm of h squared. So how to prove that? So we are guessing this is our derivative. Okay, this is our derivative at the point x, which is a linear map, a linear function in capital H. Okay, so let's find out the norm of f of x plus h minus f of x minus dxh. So this is x plus h m x m x m minus uh, xi h j I plus j m plus m minus 1. This is equal to sum over of a1, a2 up till an, where ai's are all uh, x or h. So this is one condition, that all the matrices are either x or h, and at least 2, a number of h is greater than or equal to 2. This has norm less than or equal to uh, okay. What is the norm of a matrix? So here we have something called an operator norm. Okay. So what is an operator norm? In general, it's if you have a if you have an operator, which is a function from so g is a function from a space u to a space v. Okay. So uh, operator norm of g is defined as the supremum, right? Just a minute. Yeah, the supremum of g of x, supremum of don't have enough space to write it. G of x. This thing g of x lies in v, so norm of I'm representing some the norm in v as norm of v. This is not the LVth norm or anything. So this the supremum of this such that x is in u and anything else. Yeah, and norm of x is equal to 1. Okay, so similarly, since a matrix can be thought of as a operator, so matrix is equivalent to A of a linear map from r power n to r power n, since it sends x to a of x, right? It's a linear function. So then the operator norm of that matrix will be the supremum of the set Ax, where norm of x is 1. And since all norms in the Euclidean vector spaces are equivalent, we can take this norm to be anything. So for the matrix A, so x is any vector on the unit ball in R power n. Yeah, I don't think we will be able to get any further intuition of this norm, this operator norm. This kind of some measure of the size of the matrix A or the size of the entries of the matrix A, but is not this is not same as the determinant of A or the Frobenius norm of A or anything. It's a new number, okay. And it also follows the properties of norm, that is the triangle inequality and singularity and as what do you say associativity. I mean not associativity, linearity. Linearity. So when we say like norm of this thing, we mean this operator norm. Okay, and so now from uh, yeah, so basically this follows from linearity of norms and triangular inequality. So first we can take the norm inside from triangle inequality. And next from linearity we can so just the product. I don't know how many terms are there. Okay. Okay, and we know at least two of them are h. So this is equal to times some constant. I don't care. Or not constant, we can take the maximum of all of the countable ones. Countable number of things are here. So which is of the order big O of norm h squared. This is of the order small o, I mean, this is less than small o of norm h. And that proves this is the derivative indeed. Hence f dash x is sum over xi h xj. I plus j is m minus 1. Okay, now next let's prove some theorems on the one-dimensional form of the derivative. First of all, we have a chain rule. And we have a very dirty generalization in higher dimensions of that. So the chain rule so let f be a function from a to r, a is a subset of r, g be a function from b to r, b is again a subset of r, and f of a is a subset of b. F of a is the set of all fx, so that x in a If additionally, if for all C in mm, C in if C or F is differentiable at x equals to C and G is differentiable at x equals to f of C, then I guess that's enough, right? Am I missing anything? No. So differentiable always implies continuous. So that also suggests f and g are continuous at all points in A and f of A respectively. So then we have a formula for expression actually expression for f of g of f of c, derivative of g of f of c. So g of f of c equals g dash f of c times f dash c. Okay. So how to prove it? Just so in higher dimensions, this will look something like so. Let f be from A in r power m to v in r power n, and the g is a function from v in the same v in r power m to another open interval w in r power k. Like they don't necessarily have to be in r power m or r power k or any other Euclidean space. They can be any topological space with some arbitrary name, some q. Okay, so let's not get that general. So then the chain rule Okay, and all these conditions have to hold that, like f has to be Frechet differentiable at all points in A, or yeah, and G has to be Frechet differentiable in some open interval in V, or open set in V. And then we must have G of, so derivative of G of f at x naught. X naught is a point in A. X naught is a linear map in terms of h, which is equal to the derivative of g at the point f of x naught, which is a linear map in terms of f derivative of f at the point x naught, uh, which is a linear map of h. Right. So if we get a matrix, say suppose, what will I call it, M1. If we get the matrix as the derivative of dg of f of x naught as M1, and the matrix of derivative of df of x naught as M2, then this whole thing df of x naught of h is just M2 of h, or M2 times h, since matrix multiplication is the linear map. And then this whole thing is M1 times M2 times h. So this is just matrix multiplication. So now the proof. So from our assumptions, so f is differentiable at all points in A, or did I write it V? So let me also change it to. So at all points in A, so for all x naught in A, norm of x naught plus h minus x naught minus the derivative at the point x naught, which is a function of h. This thing is of the order small o of norm h. And similarly for g we have not x naught, okay. F of x naught h, actually it's a different h, but I'm still calling it h. How does it matter? Sorry. dg of f of x naught h. So these are things which are according to our assumption. Now let us find the value of g of f of x naught. Just a minute. I have to find the derivative of g of h, right? So this takes x naught. So what is delta g of h of x naught? and this is g of, I am writing h, ff. So, it is a g of f of x naught plus some increment in the argument minus g of f of x naught. So this thing is, first we can, let's expand this one. Since f is differentiable at x naught, plus an error term which is of the order small of h of x naught. So now let us call this something, suppose t. Um, now what does this look like? This look like some point in B which is in the domain of G plus some increment which can be made as small as possible, since by like by what do you say, tweaking h, we can make the second term as small as possible since it is smaller than the order of h, and the first term can be made as small as we want since this is a linear function in h. So linear functions are always bounded above by some constant terms times h, right? Norm of h, yeah. So the whole thing can be tweaked as small as we want. So it can tend it towards 0 by just tending h towards 0. So this t can tend to 0. So h goes to 0 implies t goes to 0. So this is some y naught plus t minus gy naught. Right. So this is the form of derivative of g at the point y naught. Since we already know that y naught is f of x naught, which is inside B, where we already have assumed g to be differentiable into. So this thing has to be some derivative of g at that point x naught, which is a linear function of this t plus a small error which is much smaller than the order of t. Now, so what did we needed to show? Okay, we needed to show this was differentiable, and as you can already see that if we expand this, this is dg f of x naught, and t is d of x naught of h. Plus we have a norm of h, right? Now since well, we will apply the linearities now. So this norm O of h, so this thing is a linear function of its argument. This is a linear map, so we can break the second term off. So this is equals to dg of f of x naught of d of f of x naught of h plus dg of f of x naught of o small o of norm of h plus small of norm of t. We have to prove this is small law of norm of h. Then we are done. This is already our derivative that we wanted to show here. Yeah, this thing, this thing. So how to make it small as norm of h? What is t? What is t? Yeah, like so. If you expand the t in this expression further, we get this is our error term. Okay. Observe that this thing, this has x in it, right? Just a minute. So this thing is less than or equal to the norm of dg of f of x naught, f of x naught times this thing is a constant, so this whole thing is of the order small o of norm of norm is not necessarily, since this is already a real number. Okay, so it's just mod. So this term is handled. Now the second term. So this is again a linear map of h. So it's some constant term. So it can be bounded above by some constant term times uh, so the whole thing is less than or equal to some constant term times norm of h. But that won't be enough, right? If I divide it by norm of h, what happens to the first term? It goes to some constant. Okay, there is a O over that too. Okay, that's it. Okay. So the inside term, so the thing inside the smaller notation is can be bounded above by some constant term times norm h. So the whole thing is like some smaller of some constant times norm h. So it is some constant times small o of norm h, which is some which is just of the order of small o of norm h. So both the terms are of the order of small o of norm h. So what was it? Yeah. So therefore, del g of f of x naught equals to d of d of f of d of sorry f naught x naught of d of f of x naught h. That proves our claim. In one-dimensional case, this is equivalent to g of f of whole bar of x equals to g dash fx times, okay, since like this becomes a constant. Hmm. So it just becomes product. So f dash x, here we have an h, right? Yeah. So now we have proved both the chain rule and what else? Nothing. The only theorem that we have proved is the chain rule. Since it's already past 10, I think I'll have to stop the class right here. So as a homework, find the derivatives find derivative of f of the matrix x equals to e power x take it E for AX, or make it vector. A is n cross n matrix. E to the power some. So this is a. I don't mess with you. So this is inside R power m, right? So e to the power some vector y in R power m is defined as, or not just for y, for any matrix A, is defined as by the sum, by the infinite sum zero to infinity I factorial a power I. A power 0 is defined to be I. The next one is, now here is a matrix. If x equals to determinant of x. So x is in R power nn. I mean, the next one is, prove that f inverse derivative of f inverse at fx naught is 1 by f dash fx naught, given f from a to r. F is a 1-1 function on this open interval A, and f inverse of f of x naught, f inverse of f is, or f inverse compose f is f compose f inverse is identity map G. That is, f inverse is both the left hand and right hand inverse, and f dash x naught is not 0, and f is actually differentiable, so f is differentiable for all x naught in A. Okay. And f inverse fx naught, or should I say f inverse, is differentiable at fc or fx naught. This is the given condition. You have to prove this. Okay. This is application of chain rule. let let this be this much. Okay then. So see you next week. Bye. If you have anything to ask, you can ask. Like, okay, okay. A good night. Thank you. Bye.